Let's starting our discussion in the afternoon. The first speaker is Professor TROJA. Can you share your screen?
Sure.
Professor?
Yeah. Give me 1 second.
We can hear from you. Can you share your screen?
Sorry, I have to restart to share my screen, okay? Can you see it?
Yes.
Okay. Okay, can I start now?
Yes.
Okay. Thank you for having me today. So I will try to do a brief review of recent results on short duration gamma ray burst. So just to start, I will introduce this very popular scheme that probably everyone is familiar with. This is the canonical GRB classification in 2 classes. What you see here is the histogram of gamma ray burst durations recorded by the Batse satellite in the early 90s. And as you see, this distribution is bimodal with a minimum around 2 seconds. 70% of the population lasts longer than 2 seconds. And these are normally associated with the core collapse of very massive stars. While 30% of the observed population last less than 2 seconds. These are the short duration gamma ray bursts, and they were traditionally associated with the merger of 2 compact objects, either 2 neutron stars or a neutron star and a black hole. So this was confirmed just a few years ago by the detection of gravitational waves from a binary neutron star merger, GW170817. And you see here, this was the spectacular confirmation. You see at the bottom of this panel, you see the gravitational wave signal and its evolution in time. And you see the simultaneous gamma ray signal detected by the Fermi and also the integral satellites. And you see there is a clear increase in the gamma ray energy, in the gamma ray signal about 1.7 seconds after the merger. So this was the unambiguous proof that some short duration gamma ray bursts are indeed produced by the collision of 2 neutron stars. And following this signal, we also saw these bright optical and infrared transients that lasted for a few weeks after the merger and was consistent with our expectation for a kilonova signal, that is a transient powered by the radioactive decay of heavy elements. So what I've been focusing in the past few years has been the afterglow following the GW signal. And this is what you see in this plot is the evolution of the afterglow at different energies in X-ray, optical, and radio. And you see that at different wavelengths, the signal behave more or less in the same way. So we know that all these wavelengths are basically probing the same spectral component. And we also see that this afterglow is not like the typical GRB afterglow. It's very weird. It's less luminous and it peaks very late. So I don't want to spend too much time on this because it's probably a very known result, but just to remind everyone, this was the canonical model for GRB jets, the uniform or top-hat jets. And we can explain the weird profile by assuming that we saw it at a certain angle. But this model of jet, if seen off axis, would not explain this very shallow rise at the beginning. So this is the profile that a top-hat jet will give you. So this was ruled out as a jet model for this event, or at least disfavored more than ruled out. Another model that was discussed was the choke jet, that is a jet that fails to emerge from the ejecta and it becomes trapped from the ejecta. This model can explain the early shallow rise, but it cannot explain the late rapid decline of the afterglow. So the model that actually managed to tie together all the observations is the model of a relativistic jet, of a structure relativistic jet. So the structure is very important to explain the shallow decay at the beginning. So some people call it a jet with a cocoon, or a structure jet is more or less the same concept. What you see here are the two observational evidence for the presence of a relativistic jet. So this was the high resolution radio imaging showing that the centroid motion was superluminal. So this is an indication of relativistic motion, as we know. And the other evidence also came from the afterglow. You see, this is the afterglow temporal evolution compared with different models of cocoon and choke jet. And what you see in blue is the relativistic jet model, which is the only one predicting this very sharp decline at the end of the evolution. So I think we have very good evidence that this gravitational wave source produced a relativistic jet at the end of the merger. This is the situation after 4 years of monitoring. What you see here are the X-ray data compared with a model for the standard GRB jet afterglow. And there is a very interesting prediction that we can test now for the first time, because this event was at only 40 megaparsecs. So this is definitely the closest neutron star merger that we know. And so it's a great opportunity to test models for faint signals coming from neutron star mergers. And one prediction is the one that you see here at late times. So this is a model that was proposed by Nakar and Piran. And they suggested that, the initial signal is definitely powered by the most relativistic ejecta, but at very late time, we could see the onset of another kind of afterglow component, this late time flare produced not by the relativistic ejecta, but by the subrelativistic ejecta that powered the kilonova. So the same ejecta that a few days after the merger were producing that optical and infrared emission kept expanding and are now interacting with the interstellar medium and possibly producing a non-thermal signal visible in X-ray and radio energies. You see here our predictions for different models. So the majority of our models are actually kind of faint, so we would not, they would lie here, and this is beyond the capabilities of our instrumentation, but about 30% of the models actually lie above the Chandra threshold in this case. So that we have a reasonable chance that monitoring of this event could catch this signal. So this is these are the latest observations. So you see there are a few more points. This was this is the latest data point coming from May 2022. In black you see the X-ray, in blue you see the radio data, and you see they match quite well. What I wanted to stress here, you see there are several curves that fit the data more or less well. All these curves correspond to different viewing angle. So you can see that we can basically change the viewing angle from 25 up to 40 degrees and still have reasonably decent fit to the data. And this is because the temporal profile alone cannot really constrain the viewing angle. What we can constrain is this ratio, the viewing angle over the opening angle of the jet. This is constant among all the different curves, but the viewing angle changes. And this is important because what is telling us that we can still fit all the X-ray data with a jet model, but we are pushing the limit of the viewing angles constrained by the centroid motion from the resolution imaging. So I will go there in a while. First, I wanted to clarify that, you see there is this blip at around 3 years after the merger. There is this some sort of rebrightening. This is not the evidence that we are looking for the emergence of a radio or an X-ray flare at late time. This is, I don't know, some sort of variability. The real evidence for an excess is this deviation from the initial afterglow model. You see, as the time progresses, we need to readjust our fit and our viewing angle become larger and larger from 20 up to all the way 38 degrees. And as I say, this is a problem because the viewing angle is all as an additional constraint. And this constraint is the motion of the centroid that has been constrained through radio observations. So what you see in this plot, the error bars are the positions of the centroid derived from the radio data. And these blue curves are the predictions of the model. So if you use the latest model with a viewing angle of about 38 degrees, you can see that the prediction of the model start to push the boundary of the centroid measurements, because this prediction tends to over-predict the motion, while this prediction tends to under-predict it, sorry. But we're still within the uncertainty of the measurements. So overall, the inconsistency between the jet model and the data is, let's say, 2.5 sigma, but definitely less than 3 sigma at this moment. So statistically, we do not have a strong evidence for an additional component, but with more data, definitely we hope to grow this evidence. by using the joint constraint coming from the radio data and the X-ray data at the same time. So this is still an open question. The next thing I wanted to discuss is the environment in which we find short duration gamma ray bursts. What you see here is a collection of pretty galaxies collected over the years by Hubble and other instruments. But an initial, and as you can see, there are elliptical galaxies here at the top, and at the bottom you see a collection of nearby spiral and star-forming galaxies. So from the very beginning, I think it was evident that short duration GRBs were found not only in old galaxies, but in a very mixed environment, both star-forming, spiral, and early type galaxies. But there was this common notion that they tended to be closer than long GRBs, nearby. And this was probably an observational bias, at least in part, because we tried to focus on the galaxies that were easier to detect. But there was a large population of events without an associated galaxy. So this is the work that my graduate student, Brendan O'Connor, led in the past couple of years. And you see here an example of a hostless short GRB. We had quite a big sample of this event. As you can see, this is a deep Keck optical image. And this is the location of the gamma ray burst. And from this deep optical image, it looks like this is the only galaxy in the field that could be possibly be associated with this event. And so this is quite nearby. And you see that there is a large distance between the short GRB position and the host galaxy. So one possibility was that this event is really associated with this nearby galaxy, and it has been kicked out of its environment because of an intrinsic natal kick. However, if you carry out a systematic survey of these events, especially using higher data, you see that in most cases, not in all, but in most cases, when you observe deep enough, you will see that there is a candidate host galaxy next to the short GRB position. And the host galaxy is redder and is definitely smaller because it's more distant. And so the probability of, association is equivalent between this faint galaxy and this bright nearby galaxy. So they're both, on probabilistic argument, they're both possible galaxies, but these, in this case, this seems a more reasonable association. And why this is important is because it suggests that most of these short GRBs with no associated galaxy was not kicked out from its birth site, was actually residing in a distant galaxy at a redshift 2 or even higher than 2. And you see in this plot on my left, this is a comparison between the optical magnitude of short GRB galaxies as a function of redshift, and this is a sample of field galaxies. And you see short GRBs tend to lie in the most luminous galaxies. You see between L star and 0.1 L star, this is where the bulk of the population is found. But you see that with deep observations, we uncovered this sample of very faint galaxies. And the most likely explanation for their faintness is that they are actually located in this area of the diagram, so above redshift 1. And why this is important, you can see it in the other panel on the right. What you see here is the cumulative distribution of redshift for short duration gamma ray burst. And you see it compared with different models for the delay time distribution of their progenitors. So this dotted line that you see here is an upper limit that we can put, assuming that all these Hostless short GRBs are actually at high redshift. And so this means that any model cannot go like in this area. So our models are constrained in this area of the plot between the solid black line and the dotted line. And you can see all the blue models are actually predicting too many low redshift short duration gamma ray bursts. And so they're not a good description of the sample collected by Swift. We found that the best description for the delay time distribution are power law models with a slope between 1 to 1.5-ish. And so this is quite important because it predicts a large fraction of events lying at redshift higher than 1. And of course, it has important implications for the production of our process elements. Because if a lot of these neutron star mergers lie in the early universe, then they might be able to explain the abundances of heavy elements that we measure in our galaxy or in metal poor stars. So the last result that I wanted to discuss is the connection between long duration gamma ray bursts and maybe compact binary mergers. So there is this common idea that all long duration gamma ray bursts are produced by massive stars. I think there is growing evidence that this is not the case, but there is a small population of events that is not associated with collapsars. We discovered this over 10 years ago. There were a couple of supernova-less long duration gamma ray bursts. But in addition, in this paper, there was a very systematic survey for the locations of these odd long duration gamma ray bursts. We call them short GRB with extended emission. And you can see in this plot that shows the location of this burst as a function of the offset. You see this purple line is the typical location of long duration gamma ray burst. And this light blue line is the typical location of short duration gamma ray burst. And these odd supernova-less long GRB are in blue. And you can see they differ quite drastically from the population of long GRBs. So this is a nice confirmation because even if we don't have the supernova limits for most of these events, using their location, we can say more about their nature, and we can confirm that they're different from long duration gamma ray bursts, at least in their location. They're different from collapsars. And a recent case that is being discussed in the past few months is this long duration gamma ray burst that happened in December 2021, so no long ago. What you see here are the gamma ray light curves in different energy bands. And you see the duration is definitely longer than 2 seconds. And here on the right, you see the HST imaging of this event. It lies here, close to this bright and nearby galaxy. We don't find any other galaxy close to this position. So this event is actually very likely associated with this nearby galaxy at only 340 megaparsec. And it's another example of a supernova-less long-duration gamma ray burst. We see here our comparison between different supernova models and the limits obtained from this event. You see there are a variety of supernova models, but in general, we can say that even the faintest supernova events should have been detected with our observations. So the fact that we can only place upper limit can rule out the majority of the supernova space. So we can confidently say there was not a normal supernova following this long duration gamma ray burst. But what was even more interesting is that looking at the early time data, we found evidence for a kilonova. So this is a what you see here. These are the infrared optical UV and X-ray light curves. The dashed line is the non-thermal emission. And you see how this non-thermal emission cannot reproduce all the data, but there is a clear excess in the infrared at late time, but we can actually see it in the optical and even in the UV at early times. And so this solid line that you see here, these are kilonova models. So they're not fit to the data. These are just the kilonova light curves that were calculated and compared to the data. And you see the fit with the observations is very good. So it definitely fits this kilonova model. And here is another comparison between the data and the kilonova properties. So what you see on the left is the spectral energy distribution of this transient at different times. So we start very early at 100 seconds. We are still dominated by the prompt emission. At 1 hour, we are dominated by the non-thermal emission. And the X-ray data that you see here are always dominated by the non-thermal component. And it's only started at 5 hours that looking at the optical and UV data, we start to see this excess, which is well described with a black body component. And you can see it all the way here up to 4 days. And so if we fit this excess with a thermal component, you can see here, this is the evolution of these 4 feet. This is the bolometric luminosity, the temperature, and the radius of this thermal component. And the points that you see here in gray are the data from the 2017 GFO kilonova. And so they were compared here, and we found that the similarity between this black body component and the evolution of the kilonova is quite remarkable. So this adds, it strengthens the argument that this excess that we're seeing at optical and infrared wavelengths is actually a kilonova. And another interesting point is that because this was a GRB and we started the observation very, very soon, we actually caught the kilonova very early on in its evolution, even before our observation of 2017 GFO. They started 12 hours after the merger. But in this case, we managed to be on target even earlier. And the interesting thing is that the resulting kilonova luminosity is quite bright. It's actually a bit more luminous than what we would have expected. So it's possible that at early times, the presence of a jet has a significant impact on the evolution of the kilonova, and that's why we see this very luminous optical emission at early times, and this very hot fireball as well. I will leave you with the summary of these recent results. So I think we established pretty well that the afterglow of the GW counterpart was powered by a structural relativistic jet. And there is some evidence, but not statistically significant, that the late time data are deviating from the jet model. We don't know yet what is the cause of this deviation. It could be a limitation of our models or the onset of this new component. And only additional observations can actually break the degeneracy and clarify what we're looking at. The second thing that I wanted to highlight is that there is growing evidence that a significant fraction of short duration gamma ray bursts, at least 30% of the whole population, lies a redshift higher than 1. And this has an important implication for the delay time distribution. In particular, it favors power law models and not the typical log normal delay time distribution. And the last point that I would like you to remember is that we also managed to confirm the existence of a third class of events. These are long duration gamma ray bursts or short GRB with extended emission. And they are not associated with the collapse of massive stars. So they do not have supernova, and even the location of these events within the galaxy is not consistent with standard collapsars. And very recently, one of them displayed this significant thermal component that is consistent with a kilonova. And if that is the case, then the presence of the kilonova really confirms that some of these long duration transients are actually powered by compact minor emergers. Thank you.
Okay, thank you so much for this very nice talk. Any questions? Okay, if not, let's thanks.
Just wait a moment. So much material and beautiful result from Eleonora. And of course, it's interesting as the GRB 1708, 17A presented this data evolution still today, and the data are building up. And I think that Holger Weda, maybe tomorrow, will make a remark on this. And we are still getting organized for the rest of the program. The short GRB, you know, we had worked on short GRB ourselves. And in the early days, we pointed out with a phenomenological model that indeed some of these short GRB are systematically at larger cosmological distance than we had expected. And it will be which was expected. And therefore, this is a point on which we will come back to you with our previous result and see this very, very interesting result and how it fits with the evolution of BDHN. And the fact that all long GRB do not arise from collapse also is very interesting. And I urge you possibly to be here at the talk tomorrow. Eventually, we displace the talk around this time tomorrow of 1U, where you will see something totally new about the jets versus synchrotron of new neutron star, which has been we are just preparing a press release.
Okay. Any more questions? Oh, if not, let's thank the speaker again. Let's move the next speak.
May I ask something to Elena in the meantime?
Who is the next speaker?
Is Eleonora still around? I would like to ask
I'm
something.
here.
Ciao, Eleonora. Just about this delay time distribution of the short GRBs. So what did you expect something different from a power law for that distribution?
Sorry, what do you mean?
Because I mean, you say that it's consistent with a power law and not with a log normal distribution. So you expect that to be more consistent with the log normal or with a power law?
Well, it depends. The log normal was actually the favored model for a very long time. So I think the log normal was the best fit using the early data from short GRBs. And, you know, even if you look at works published in, let's say, 2015, the log normal seemed to be the favorite model. But with, I think there was a huge observational bias due to the fact that we were basically following the nearby galaxies because they were closer, and therefore their distance was easier for us to measure. So to identify a distant galaxy, it takes much more observing time and is just more challenging. So people didn't do it at the beginning. I don't know if that answers.
Hello? Hello? I don't know if you heard what I said, Eleonora.
I heard most of it. I think at some point you got offline. But I think we heard pretty much everything.
Okay, I just reconnect. Can we reach you tomorrow? And anyway, we will indicate why at the moment in which in the program, the most important result will be presented. And I think this will be quite important. And thank you for the nice data.
Thanks to you. Bye.
So I'm looking for the next speak. Or maybe we need to have a coffee break.
Yes.
Okay. Okay, let's move the last speak. Professor Bin Zhang will give our last talk today. Okay, Johnson.
Okay, let me share my screen. Can you see my screen?
Yes, yes.
Where's the full screen? Okay, here. Okay, thanks Remo and everyone for the invitation. And thanks Leon for the chairing the session. Yeah, I was supposed to be at the meeting, and I tried to apply for the visa, and just took so long. So I have to do this remotely again. But I'm going to introduce the subject of fast radio bursts, which is a new type of radio transient. So let's start with some observational properties, and there are many review papers, and myself wrote 2 of them, and the material of this talk is mostly based on these 2 papers. And we start with the temporal properties. So these FRBs have short duration, typically milliseconds, and just if you multiply by speed of light, that give you the size of the engine, which is roughly 3 × 10⁷ centimeters. Not many objects can be this small, so only neutron stars and stellar mass black holes can do this. So this narrowed down the origin to neutron stars and black holes. But still, we don't know exactly what is happening. And if you look at internal structure, the very first FRB, there's just 1 single spike. But later on, more FRBs were discovered. You can see there are such kind of temporal structures, which means in each burst, you can have multiple episodes. And for some of them, like this one, you can see a clear longer tail than the rising phase. This is dominated by scattering, the propagation of the radio waves across the interstellar medium, likely in the host galaxy. And repetition, at least some FRBs repeat. I think the published FRBs now probably several hundreds, definitely more than 500. But the repeating sources are probably about 20. But there's some arguments saying that maybe the majority of, if not all, FRBs repeat, simply because even though some of the FRBs are not repeating, you don't know whether it will repeat tomorrow. And the event rate is so high, we just don't have enough catastrophic events in the universe to power all the non-repeating FRBs. But some of these repeating sources have a very high repetition rate. The highest recently we used FAST to observe 1 source. Within 1 hour, we detected more than 500 bursts, very high repetition rate. However, some of them, like the very first one, this Lorimer burst, people followed up with hundreds of hours. There's no repetition. So possibly observationally, there's the dichotomy between repeaters and non-repeaters, apparent and non-repeaters. For example, the pulse width, the repeating bursts seem to be broader, wider, and the non-repeating ones are narrower. And in terms of spectrum, the repeaters also show narrower spectrum than the non-repeaters. But we should say that some of the repeaters also look like a non-repeater, so that's why we cannot rule out that so-called non-repeaters are repeaters. Periodicity. People tried very hard to search for like neutron pulsar-like periods from milliseconds to seconds, and found none. So there's very strict upper limit, tight limit of the periodicity. However, surprisingly, there was 1 source that had a 16-day quasi-period. So that is very puzzling, and the leading interpretation is probably they're in a binary system, or maybe the magnetar is precessing. Move to the spectral properties. These guys have been detected from 110 megahertz all the way to 8 gigahertz. Spectral shape, for apparently non-repeaters, it looks like power law, but if you look at repeating bursts, they are they have a narrower spectrum, looks like Gaussian type. Very interesting property is called frequency downdrifting. So these plots are usually called waterfall plots. So this is frequency and this is time, frequency and time. So you can see for individual bursts, so these are two repeaters. This is the first repeater, second repeater. You can see the burst is composed of multiple peaks, and the high frequency ones arrive earlier and low frequency ones arrive later. They're all like this. This one is particular clear. You can see this is drifting, down drifting. Sometimes it's called sad trombone effect. This is very popular, and this is the fast results. The majority of bursts from this particular source, we detected more than 2,000 of them. They have this down drifting behavior. Polarization. For most of the bursts, they're nearly 100% linearly polarized, but circular polarization has been detected in some of the bursts. And for linear polarization, if we measure the position angle, so this is a linear polarization position angle, in some cases, we can see it is flat, which means during one burst, this is very short period of time, it's just 1 millisecond, just stretched out. So you can see the polarization is not changing. So, however, this is a repeater. And in some other case, this is another repeater observed was fast. You can see clearly this one is more or less flat, but this one is rising. This one is dropping. This is flat and rising. So clearly more complicated signature of polarization degree variation. Yes. Remo, did you say something?
No, it's okay.
Yeah, okay. So once we have polarization, one can measure something called rotation measure, which measures how the polarization angle varies with frequency, and physically it is related to the integration of B parallel magnetic field along the line of sight and multiplied by the density. And observationally, very interesting, this RM is varying. This is RM panel. You can see within one burst, it goes flat and rise and go down and rise and down. So it's very complicated behavior. This is probably telling us something about, because density cannot vary that crazy along the line of sight, the entire line of sight, because the density is mostly dominated by the intergalactic medium. But B field can be very strong near the source. So this rapid variation is probably telling us there is a dynamically evolving environment right next to the source. And dispersion measure, so for every FRB, one can measure DM. DM tells us the column density of the free ionized electron along the line of sight. So DM is, so okay, so this is the galactic latitude. These are the pulsars. You can see the majority of the pulsars, this is the galactic plane, this is a higher galactic latitudes. Their DM is of the order, if you go to higher latitude, it is order several tens. However, these are FRBs. They are detected majority of them, they're not in the galactic plane. They're at the high galactic latitudes, and their DM is much higher, hundreds to thousands. So immediately this tells us these guys are not from our Milky Way galaxy. They have extra free electrons along the line of sight. And this extra DM is consistent with their distance. So there is a simple relationship between this DM IgM and the redshift And it turns out observationally, it really shows that if you have a higher excess DM, then you have a larger redshift. So this tells us that FRBs are from cosmological distances, And right now, the measured the redshift go up to 0.7. With the measured redshifts, one can measure the luminosity and the energy of the FRBs, isotropic value. Even for those without redshift measurement, you can use DM to estimate the redshift. You can also estimate the energy and luminosity. It turns out that the peak luminosity is in this range, 10 to the 38 to 10 to the 46. And the isotropic energy, because the duration is milliseconds, energy is only this range. So this is small in the GRB standard, much smaller than GRB. However, it is much brighter than the radio pulsars. So in the radio sky, these are the brightest objects. Of course, if you consider beaming, we should consider some FB parameter, delta omega over 4 pi, and the true luminosity and energy should be smaller than this factor. However, there should be many more those FRBs not beaming towards us. And another interesting parameter in the radio community is the brightness temperature. So basically, this is a combination of the luminosity and the duration. It just tells us that, okay, suppose this radio emission is from a black body. It is definitely not from a black, but if it is a black body, how high the temperature should be? And the answer is the temperature is 10 to the 36 Kelvin. That's huge. So this also means that because it is not a black body, then we need to have something special, which is called coherent radiation mechanism. So all these radiation needs to be emitted coherently. Very interesting comparison between FRBs and GRBs in these two fields. Very interestingly, the two fields went through the process of answering these 4 questions, and FRB field had a shorter path. So the first question is, are they astrophysical? In both fields, it took about several years to figure out from first discovery, and then with some doubts, are they astrophysical? And eventually they have firm evidence that saying that they are astrophysical. And the second question, are there multiple types? In the GRB early years, there are repeaters and non-repeaters, long and short. Interestingly, FRBs have repeaters, but now we don't know whether or not there are non-repeaters. Where are they? For the GRBs, the repeating ones are nearby in a galaxy or nearby galaxy, but long GRBs and short GRBs, they're both cosmological. And FRBs, we now know that they are cosmological. However, we detected one galactic event. I'll talk about that later. And what makes them is also took many years. We need some smoking gun observations. So for GRBs in '98, we detected a supernova associated with GRBs. So we know they're related massive star core collapse. And short GRBs, 2017, there was association with gravitational wave event. So likely they are related neutron star mergers. And for FRBs, it was the galactic one eventually told us that magnetars can make FRBs. But we don't know whether all the FRBs are made from magnetars. There could be some other sources as well. And this is another interesting comparison between the two fields in terms of the years since the first discovery and the number of papers published. Note that, so this is the GRB and this is the FRB. And so the FRB papers published more in a shorter period of time. So in the FRB field, the temperature shrinked by a factor of 2, and total number scaled down by a factor of 0.4, and they looks like matching well. And this is a projected prediction for the FRB field in the future. So there should be more papers published in this field. And working in this field is a lot of fun, just like detective approach. So we are looking at fingerprints, footprints, sometimes smoking guns, and trying to figure out the crime scene. And what may make them? This is an incomplete list. I think right now there are more than 50 models. This is with no particular order. But what I'm trying to say is that just like in the early years of GRBs, people are initially just guessing, and this one thing happened. So before this event, it looks like a wave function in quantum mechanics. There are probabilities, all kinds of outcomes. But then the wave function collapsed. So we found one FRB from the magnetar. So the magnetar model suddenly becomes the dominant model. And some people even believe that all the FRBs are produced from magnetars. So this happened in April 28th in 2020. There was a soft gamma repeater, a young magnetar. And that magnetar produced a lot of gamma ray or hard X-ray bursts. One of them actually had a FRB associated with it because they're in the radio in the Milky Way. So those two radio bursts were extremely bright, so mega Jansky level, and two peaks, and one of them was also detected by STER2. So this is ZHANG, this is STER2 detection. And very interestingly, there was an X-ray burst associated with it. And this X-ray burst also had some spikes, some peaks. Interestingly, there are two hard peaks. And those two peaks, the separation between the two are consistent with the separation of these two radio bursts. So it looks like these radio bursts are associated with these two peaks. Okay, so now move on to models. How do we understand this? So FRB models in general have two components. One is related to the source, whether they're magnetars or something else. The other one is regardless of the source, what is the radiation mechanism of radio emission? So this is the coherent radiation mechanism models. So these models can be applied to several different sources, and each source can probably have these multiple mechanisms. So this is a separation. Some theories work in this direction, some theories work in this direction. Yeah, for coherent radiation mechanism, there are two dominant categories. One invoke emission inside the magnetosphere, so I call it pulsar-like. The other is outside magnetosphere, looks like GRB. And source models, we have repeating and non-repeating. And so for each category, we have some subcategory. I'll try to get some of those later. And you can see these discussion, the models, there are two types. So people can either go from this direction. So this is bottom up, start with a particular mechanism and try to interpret the GRBs. The other approach is start from observations and try to ask ourselves which one is correct. I think this approach probably will have a higher chance to be correct. So this is a top-down approach or a detective's approach. So the rest of the talk, I'll use this approach. So the physical mechanism of FRB is a detective's approach. So we started with observation and do some constraints. The first one, the duration is milliseconds. As I said, the engine size can be this. Of course, the real emission region size can be larger by a factor of gamma square. However, if you really go back to the source size, it is essentially speed of light times variability time scale. So this is related to the propagation delay of the light from the two ends of the engine. The second one, the energetics, radio efficiency, and beaming. The isotropic luminosity energy is in this range. If you introduce the beaming factor, we should also introduce efficiency, because radio emission might be a small fraction of the entire emission spectra. So we divide by eta -1, and eventually we can get the true luminosity and energy. Then for one-off bursts, beaming make it smaller, and the efficient makes it bigger. For repeaters, we have to consider the distribution of the luminosity and energy. Eventually you get a total average luminosity. So these are some basics, but if you really plug in the numbers, and we are limited to some of the energy sources, for example, the magnetic energy, spin energy, gravitational energy, kinetic energy, and we have some significant constraints on some of these possibilities. The brightness temperature, as I said, is of the order 10 to the 36 Kelvin. It tells us that the emission mechanism has to be coherent, simply because these are the black body. And if we really talk about association in the radio band, the radio emission is somewhere here, way above this black body. So it means here is self-absorbed. This thing is not self-absorbed, must be extremely bright, and we need to have certain coherent mechanisms, including bunches, plasma masers, and vacuum masers to do this. And this plot gives you an idea of different radio transients. So this is the frequency, this is the luminosity, and this region is where the incoherent radiation is. Everything above this line should be coherent. You can see the radio pulsars are here. They are already quite coherent. However, FRBs are here. So they are the most extreme coherent radiation in the universe. And very general constraints in order to detect FRBs on Earth. The fast radio burst, the coherent radio emission, must overcome some of the absorption processes along the line of sight, especially near the source. So one of them is induced Compton scattering, the other free absorption, or single chamber absorption if there is a nebula. So there are many papers talking about these. And once they finally escape, then we can start to figure out the physical mechanism, what generated those bursts. So I'll talk about the radiation mechanism. It's hard to, because we haven't really had a clear clue about how FRB is working. So we can go to the two neighboring fields, GRBs and radio pulsars, and use the lights of those two fields to understand FRBs. So lessons from the GRBs. The GRBs, along to relativistic outflows, we have internal and external shocks, and some ideas, some people back in the GRB field, they think that there might be this in the relativistic shocks. If the B fields are ordered, there might be coherent radio emission. So those are called single chunk masers. So some of those ideas have been borrowed to interpret FRBs. So this is the Metzger model saying that FRBs are produced in the magnetized relativistic shocks. And for radio pulsars, we do know that radio pulsars can emit radio emission from the either polar cap region or in the outer gap, or even near the light cylinder, or even outside the light cylinder from the current sheet. And so from observations, we know some radio emission aligned with the gamma ray emission is probably at very high altitudes, and some of them actually in the inner magnetosphere. So these two models have been, two ideas have been introduced to FRBs. People developed two types of models, pulsar-like and GRB-like. In the pulsar-like scenario, we introduce a magnetar with some cross-cracking and sending out some alpha waves, and the alpha waves in closed field lines will heat up the plasma and radiate X-rays and open waves in the open field line regions will reach some charge starvation region and produce radio emission there. And in the GRB-like model, everything is far outside the magnetosphere, but in some relativistic shocks. So these are the two types of the models. And for each model, there are multiple submodels. And these two different models actually predict different properties in terms of beaming angle. So pulsar-like models, because they're in the open field line region, the emission is probably narrowly beamed. A GRB-like model might probably have wider beam. Radio efficiency, GRB model is quite inefficient, and the pulsar-like model can be efficient. So this one predicts brighter X-ray and gamma ray emission, this one not. And in terms of polarization, that's very interesting because this model, in the shock model, all the B field needs to be straight ordered. So they have either no polarization or very high linear polarization with a constant polarization angle. But this one, because it comes from the magnetosphere, the polarization angle can change. So this polarization properties as a clue, as I said, some of them show a flat polarization angle. So this can be interpreted with this model, or the magnetosphere model if the emission region is very far away, is outer part of the magnetosphere. However, when you start to see this varying polarization angle, then it suggests that we really need to introduce a magnetosphere because a line of sight will go through different regions, sweeps across different field lines to have this varying B field. And this is another interesting observation from FAST. So we detected more than 1,500 bursts from this particular source. And there's a distribution of energy and also distribution of waiting time. So you can see it's very high repetition rate, a very short waiting time. Some of them just need only wait for tens of milliseconds if another one comes out. So this is also difficult for the shock model to do. And in terms of total energy, if we only add up the radio energy, it is still reasonable. However, if we consider the low efficiency of the shock model, if we introduce another 4 orders magnitude energy go to X-rays, then the total energy is huge. It's already a substantial fraction of the magnetar energy. So this is another evidence against this shock model. The downdrifting feature is very interesting. It is easy to understand within this magnetosphere model. If you have curvature radiation, the same blob moves away. So in early on, you observe same set of blobs move outwards. When your line of sight start to go through the different blobs, you always catch them at the lower altitude to begin with and see the higher altitude ones where the emission frequency goes down. So this is easy to understand within this scenario. Okay, so again, back to this SGR FRB X-ray burst association. We know that at least some FRBs are produced by magnetars. Then how to produce that? As I said, we should have a magnetosphere. So the standard picture is a curvature radiation. Another alternative picture, which I published recently, is through inverse Compton. So the idea is the following. Again, we can have alpha waves to accelerate particles here. However, instead of let these particles do curvature radiation, we can just upscatter these low frequency waves, which is associated with the cross oscillation, just like the alpha waves, and then upscatter this to higher frequencies in the radio band. This is another possibility. And in the literature, there's also a criticism about all these magnetosphere model saying that the scattering optical depth is so high because these waves have very large amplitudes. However, they introduce scatter in the closed field line region. If we consider open field line region, if we consider the particles that the plasma is moving outwards, then this is no longer a concern. So this paper recently addressed this concern. Very interesting fact is that even though we have one FRB that is associated with the X-ray burst, but the majority of X-ray bursts, in this paper, we reported fast observations, stared at the magnetar for many hours. And in 1 hour, there were like 30 other X-ray bursts came out, but there's no radio image at all, let alone FRB, nothing. So this is very tight constraint, stringent limit. It tells us that the majority of X-ray bursts are actually not associated with FRBs. Then one possibility, so there could be several possibilities. One is this X-ray burst is just special, and the other bursts are not that special to make FRB. And another possibility is, okay, maybe every X-ray burst has a FRB associated with it, but FRB beaming angle is very narrow. Only this one had FRB beam towards us. In other cases, they beam elsewhere. So within the second scenario, we can produce something called slow radial bursts instead of fast radial bursts. So these are the off beam, just like in the GRB scenario. So we have relativistic jet going this direction. When our line of sight is outside this jet cone, we probably will see something lower with lower luminosity and longer duration, like in the case of the short GRB associated gravitational waves. So here, something similar. We can have slow radial bursts, which have a longer duration and the lower luminosities. So I investigated this possibility and look at the data. There might be one case that is like this, but the majority of cases, they're not. So this potentially gives some constraints on the geometry of FRBs and whether or not all the X-ray bursts are associated with FRBs. Okay, so we'll move on with some open questions. So where is FRB emission generated? So are they from the magnetospheres or shocks? What is the coherent mechanism? So I already talked about this. So my favorite scenario based on the available data suggests that they should be from the magnetospheres. And the coherent mechanism is still not well understood. It's curvature radiation, inverse Compton, or other plasma instability coherent mechanisms could be all possible. Are there engines other than magnetars that power FRBs? This is very interesting because the current some of the properties of what we see cannot be fully understood within the magnetar scenario. So if so, what could be the plausible sources? And finally, are there generally non-repeating FRBs? If so, what could be the plausible sources? So these are there are many open questions. I think these three are the most important ones and widely discussed in the community. So this talking about two different types of sources, these are two extreme versions of source models. In the optimistic case or in the conservative case, one can say that all the FRBs are produced by magnetars. So within this scenario, so we have regular repeaters and apparent non-repeated. We also have active repeaters. There are two types of observed FRBs. For regular repeaters or non-repeaters, we can invoke something like the magnetar in our galaxy. We call these regular magnetars. For active repeaters in our Milky Way, we don't have an active FRB repeat source. So these active repeaters need something special. If they're related to magnetars, they need some special magnetars. For example, do we need a long GRB progenitor, superluminous supernova progenitor, neutron star neutron merger progenitor to make some young magnetars? Actually, recently I'm also thinking along an opposite direction. These active magnetars might be related to old magnetars, reactivated magnetars. So this is the most conservative case. So everything is related to magnetars. And another this is pessimistic and conservative. This is optimistic and crazy, I would say, type of the idea. So there are so many different types of FRBs. So we have not only repeating FRBs, we also have generally non-repeating FRBs. And for repeating FRBs, besides magnetars, we have other things. For example, neutron star pre-merger, magnetosphere interaction, black holes, white dwarfs. And for generally non-repeating FRBs, we have compact binary mergers, blazars, black hole evaporation, other possibilities. So probably nature won't have like 50 ways of making FRBs, but probably it is too simple just to have one mechanism. Something in between, so probably 2 or 3 types can make FRBs, just like in GRBs. We know that definitely it's not one mechanism. There could be at least 3 or more mechanisms to make GRBs. So future data will show this. So I want to emphasize a little bit scenarios of FRBs that are connected gravitational wave sources. So one possibility is that the 2 neutron stars, this is the before merger, even decades or even centuries before the merger, the 2 magnetospheres are already interacting. There are friction, there are probably reconnection. Those will sometimes will accelerate particles and probably make FRBs. And during the merger, if one of the sources charged, especially a black hole and a neutron star is charged, the neutron star got swallowed by the black hole, and very naturally it can make a brief, something like a FRB, short EM counterpart. And finally, if the neutron star merger leave behind a supramassive neutron star, which does not collapse to a black hole right away, it takes some time, maybe hundreds of seconds or even hours after that. And when the neutron star collapses into a black hole, the magnetosphere is ejected, and then a FRB can be produced. In this case, the FRB will be followed by a gravitational wave event. So the scenario is as the gravitational wave chirp event, and this one is before and this one is after. So this should be very interesting to look at in the future multi-messenger observations. Okay, so I think use up my time. This is a summary. So coherent radio emission model, talk about location, magnetosphere versus shocks. Source models, I talk about the most conservative and speculative scenarios, and prospects. From observations, I think galactic FRBs hold the key to identify sources, just like the one we detected. We immediately knew that, okay, it was from a magnetar. So maybe in the future, some other galactic FRBs could be detected, probably from another magnetar or probably from something else. And also multi-messenger observations, as I just said, gravitational wave versus FRB joint observation should be very important. And then from the theory front, there's still the debate of coherent radiation mechanism will continue, and a lot of magnetar physics need to be studied, and physics of other systems should be also studied in order to understand better the mechanism of FRBs. Okay, I'll stop here and thank you very much. And I'll take questions.
Thank you so much for the very nice talk from Professor Bin Zhang. Any questions Any questions?
Well, I would like just to congratulate Ping Zhang of this fantastic review and all the splendid data that are coming out also from the observatory in China, which is really becoming at the forefront of this research. And it's very good that he guides the understanding of the system, which as usual, they will be, once they will be understood, something totally unexpected and new, I presume. Congratulate again.
Thank you, Rebecca.
Any more questions?
May I ask?
Sure.
Okay, thank you for very nice talk. Actually, my question is coming back to that point you mentioned about changing the polarization angle.
Mm-hmm.
You said from the GRB explanation, we cannot explain that. However, we know maybe due to some geometrical effect, when the observer is off axis to the GRB, then we may observe this change of this polarization angle.
They probably will have a different polarization. So you're saying that from instead of observing this direction, you look at other directions.
Exactly.
But because the
B
B field,
you will see this jump.
Yeah, but the B field has to be straight in the emission region. So I think viewing from other angles will make it fainter, may not be FRB. Even if you can do it, globally this polarization angle should change. However, we won't expect that within this burst, it will go up and down because the B field itself is ordered. In this scenario, it's different because the line of sight is looking at different parts of the magnetosphere, different field lines, so you can start to see this. So yeah, I think it's still difficult. The colleagues who proposed this model, they also thought it very hard. One possibility, they're trying to introduce the variation of upstream B field, which is varying significantly, but still the duration is only millisecond. There's a millisecond. Within a millisecond, the upstream B field sweep wildly is very unlikely.
Okay, thank you.
Thank you.
I see there are another questions.
I think Wahid has a question.
Yes, big thank you. This is very nice. You covered all the important points of this interesting subject. I want to make one comment that I have one question.
Mm-hmm.
The method I described yesterday for looking at the cosmological evolution of gamma ray burst, we have recently applied it to FRBs, and some preliminary result we are not ready to publish yet. I just thought I'd mention it. It looks like the formation rate of GRBs, FRBs, is more like a short gamma ray burst.
Yes, exactly. Yeah.
Delayed relative to star formation rate. So
So glad you guys
our hypothesis.
Right, glad you guys got that because we also found that, and there are other papers also. Yeah, so looks like the DM distribution peaks at a smaller value than what the star formation rate is predicting. So yes, I'm very interested at looking at your paper.
Yeah, when we are ready to publish, I'll send you one. The other thing I want to question essentially, I missed your last point about the merger and FRBs coming after gravitational wave. That will, after black hole is formed, that will be closer to GRB model rather than the magnetospheric model that you were proposing as more likely.
You mean this one? This one is the following. This is the GRB light curve. So you probably remember that some of the GRBs, these are especially short GRBs, they have short gamma rays, and then there was an X-ray plateau, and this plateau lasted for about 300 seconds, and suddenly it drops like a stone, so very steep. And we interpreted this X-ray plateau as the collapse of a supramassive neutron star after the GRB itself didn't make a black hole right away. They make a supermassive neutron star, and that neutron star stay alive for a while. But because it's spinning down and eventually the centrifugal force can no longer, centripetal force can no longer sustain the gravity, and then it collapses to make a black hole. But because of the no-hairs theorem, the closed field line magnetic fields cannot fall into the black hole. It just got ejected. And pairs, something like pair production, cascade, and coherent radiation might happen to produce an FRB. So in this case, the emission mechanism probably, as you said, is not strict like the magnetosphere model, because the magnetosphere itself is moving away. I should say there's no detailed radiation mechanism model for this one yet. But I should also say it is not public yet. So we had a paper collaboration with the Australian LIGO people and FRB people. We actually found one FRB actually follow one of the binary neutron star merger, and it is quite consistent with this scenario. So the paper is currently under review at Nature. It will be posted once there's an outcome.
Yeah, making coherence radiation may be difficult in this situation.
Yeah, in this situation, yeah, maybe more along the line of the shocks may be better. But still, we haven't really studied it carefully yet. Yeah, so maybe something along the line of particle acceleration in the ejected magnetosphere probably will also work. But I agree with you; it's no longer straightforward.
Yes, thank you very much.
Thank you, Mary.
Okay, any more questions? Okay.
There was an old paper I did with Luigi Stella about coherence radiation coming from maser. And it will be very interesting to see, but this is just an idea which eventually will come back. Let me thank everyone for this. Now, in a few minutes, I will send to everyone some material which will be important for the 2 sessions of the next 2 days, in which we will present very new results, and we can send you 3 papers to look at. One will be put on AstroPH today, and you can read right away. And then we will have tomorrow around this time a general discussion following the new program, which also I'm sending right away. Therefore, I stop here in order to be able to make this mail right away. And thank you everybody for this beautiful and fascinating discussion, and congratulations to everyone.
Okay.
Thanks, Rima.
Okay. Thanks, Professor Binzhang again, and also thanks all the speakers today. Professor Feeling, maybe we can stop here today.